Give it up for Abro.
So hi, my name is Abro. So a little bit about me. I'm gonna be a senior in high school when the summer ends, and I go to high school in Lynbrook High School in San Jose, California. And yeah, that's my GitHub and my Twitter, in case you guys want to know. Okay, so I've been interested in chess for a long time, and I really wanted to create a chess engine. And since I knew Python, I figured, why not? So there are a couple ways to do this. First of all, you can theoretically brute force chess. So like just calculate every single move and every single position on the board until victory. But I hear some of you guys laughing. Yeah, there's like 10 to the power 43 moves out there, so you're gonna have a bad time with that. Conventional chess engines, therefore, they kind of quote unquote hard code it in terms of like a lot of there's when a chess engine looks at a position, it'll look for certain tells like doubled pawns, king safety, or things like that in order to determine if the position is beneficial or harmful to a certain side. And so the problem with this though is that if you strategies evolve, and obviously different people have different ideas of what means what, and so this becomes really hard to maintain now because you have to keep changing this code in order to look for different tells on board, in order to look for different signs of how a position is. So, and on top of that, these two don't work particularly well in Python because Python isn't the fastest language out there. So you'll see most chess engines nowadays use C++. So yeah, I'm not learning C++. So I figured, why not use machine learning? So let's back up a bit. So essentially at a core, chess engine is a function that converts a position into a move. So in order, the way it does that is it looks at all the possible moves a player can play, and then it selects what it thinks is the best move and chooses that. But there's a problem, and let me show you what I mean. So first of all, the way it does that is that it uses something called an evaluation function. An evaluation function looks at the board and determines how good that position is for a certain player. So then chess engine can look at all the positions that will result from someone playing a move and then look at which is the best one and play that move. So the very simplest one is using piece weights. So I don't know if you guys know, but like a pawn is worth 1, knight is worth 3, bishop 3.5, so on. And you can add your pieces and subtract your opponent's pieces and get like a net value of how good a position is for you. But let's play a game for a while. Okay, so imagine that it's me versus all you guys. So you guys are trying to get the highest number, and I'm trying to get the lowest number out there, okay? And how this works is I start at 1, and then I either go left or right to level, I start at level 0, and I go left or right to level 1. And after that, you guys go left or right to level 2, and then I go left or right to level 3, and so on and so forth. So I'm trying to reach the lowest, you're trying to reach the highest. So initially, it might look like the best position to play is go towards that -10 right there, because that's a lower number than -7. But then if you look even further, you'll see that that doesn't lead to any good results, because on that side of the tree, all the numbers are higher than on the other side. So if you were smart, you'd go to the other side at -7, because even though it looks like that position's worse, if you look further down the line, you'll see that that position's actually better. So that's the, it's something really, really similar in chess, because chess works in a similar way. So in order to accomplish the same feat, we have an algorithm called Minimax. So Minimax, this is a code example, but Minimax essentially recursively goes through the move tree and looks farther, a couple moves ahead, and then decides like, hey, is this position, which is the best position for me, assuming my opponent plays well. So this is like, I'm not going to explain that code word line for line, but yeah, that's the code if you want to like see it. Okay, so back to evaluation functions. right? Because Minimax still needs an evaluation function, right? Because you still have to evaluate the board even if it's 10 positions in the future. So the problem is, again, as I mentioned earlier, a lot of it's like handcrafted because chess engines look for certain tells of what's a good or bad position. And that's sort of a hard-coded way to do it. And as well as that, you need like chess experts on your side in order to determine those tells. So if you're a normal programmer, like it's kind of hard to do that. So enter TensorFlow, Google's library for deep learning. And TensorFlow is, obviously a very amazing library because you can do deep learning really easily in it, and it's also pretty fast. So basically, I built a neural network, and this is like a basic description about what it does. But essentially, it'll take an input, in this case the board, and feed it through a series of layers which consist of neurons, which kind of fire depending on what the input is. So then the output will be like if the position is good for you or good for the opponent. And now a neural network, essentially it requires a lot of data. You have to like give it a bunch of data of positions that are good for you, good for the opponent, and then it'll tweak itself in order to match that and create a sort of a model. So to basically solve the problem. So training data. Obviously, I mentioned you need a lot of training data. Luckily, chess training data is really, really easy to get. So there's a file format called PGN, which let me just show you an example of. This is like a very basic example of a PGN. Oh, wait, oops. Okay, whatever. Let me do this. There, can you see that now? Wait. Okay, whatever. So essentially what a PGN is here it was. Okay. So essentially what I wanted to show you guys was that a PGN is essentially a text file. And it contains all the moves written in algebraic notation one by one. So like E4, E5, and so on and so forth for a bunch of different games. So the nice thing is since it's a text file, we can open it in Python and really easily convert it into like a move that the computer knows and then feed that. So how I fed it in was I assumed that because I got like a game from a bunch of grandmasters that they're gonna play right moves. So after the grandmaster, like after somebody moves, I'm assuming that that position that results in is better for that player. So like if white moves, then I'm going to assume that that position is better for white. And then if black moves, then I'm going to assume that that position is better for black, and so on and so forth. There are exceptions, like I look for extreme material deficits, meaning if somebody's obviously doing worse depending on material, I'm not going to count it for better just because that player moved. So that results in like a really, really big training set that I can use, which is really nice. So, okay. So here, to get into a bit more detail, these are the features and labels. So the input is an 8x8 array representing the chessboard. And I'm storing the pieces as their worths. So like a rook will be stored as the number 5, a white rook, and a black rook will be stored as -5. And a white pawn will be stored as 1, say, and a black pawn will be stored as -1. So essentially, what that means now is that like I have an 8x8 array of a bunch, mostly zeros, because most of the positions on chessboard are unoccupied, but with a few negative numbers and positive numbers. And then the output will be a one-hot vector, meaning like a vector in which which consisting of two elements in which either the first one is 1 or the second one is 1. So if the first one is 1, then that means it's black. If the second one is 1, it means white, as you can see up there. So like 0, 1 is white, and 1, 0 is black. So that's the output of my whole neural network. So now I have to construct a neural network that converts that to that. So I decided to use a convolutional neural network, because a chessboard in some ways is a lot like an image. So convolutional neural networks do really well with analyzing images. And what they do is they kind of look at different parts of the image and run convolutions on them and like kind of simplify them to look for distinct features. that can be used to determine whatever it's trying to determine. So specifically, my neural network consisted of 2 convolutional layers and 1 fully connected layer, which is just a normal standard layer in a neural network. So here's kind of the graph of it. It looks a lot prettier. So you can see that there's con 1, con 2, and then the fully connected layer, as well as some other things that I generated this using TensorBoard. So yeah, here's the code. I wanted to show a snippet of it. So I also used dropout, and what dropout does is it tries to prevent overfitting of the model. So it'll like randomly drop some neurons in order to make the thing a little more randomized. So that way, the model will try to fit to, it will kind of generalize the situation and try to fit to what's important, and not look at little bit of like the noise in every model, because there's going to be a certain amount of noise, and you don't want to fit to that noise. You want to fit to the essential relationship. So dropout kind of helps with that issue. Whoa. Okay, so a couple of feature improvements I'm going to make is, number 1, like right now, the thing is pretty slow, which I want to show demo. I don't know if I'm going to get that to work, but basically, so that allows. I want to make it faster, and hopefully I'm going to write some things in Python later, because Python is still like slow with some of the computational stuff, and I also want more training data. So the issue is, like right now, I'm not using that much data in a PGN, so like, there's loads and loads of chess data out there, so I have to like curate each one and make sure it's like actually like good games, and there's a wide variety. And I also want to build features to let the chess engine play itself. So the problem with playing chess engine playing itself initially is that it can get, if it doesn't know anything initially, it can't do much. So I want to kind of get it up on a good footing with data that already exists, and then have it train itself from there. Okay, yeah, that worked. So I want to show the demo. I'm not sure how to exactly. Let's try this. Nope. Oh, here it is. Okay, awesome. Okay. Whoa, how do I? Okay. Let me see if I can mirror this. Oh, here, there, that's better. Okay, now I can show you guys what I wanted to show you guys. Okay, so here's what a PGN looks like. So as you can see, it's just a bunch of like moves written in algebraic notation with some metadata, with like some 1s and 2s for, so kind of I have to parse this out and get rid of all of the numbers and the metadata, and like just purely feed the moves into the engine. So now I want to show you guys a demo. So here it is, like running right here. So like if I don't know, what move do you guys want to play? Which one? Queen? Queen pawn d4, okay. Take a while. Okay, so it decided that was the best move, probably because to it. Everything is like the same, like initially. E4, okay.
So it's searching through its database right now. It's not experimenting, right? It's using a neural network that's already been trained. Right?
Yeah.
Gotcha.
But the issue right now is the fact that to it, since the data is not like, it's having a hard time with openings, as you can see obviously with this current moves, because with openings it's harder to tell whether position is good for you or good for the opponent because there's less material loss.
Right.
Like for instance, you wouldn't want to move an edge pawn like that, like if you were a human usually, but the computer, it's all the same because you're not losing anything by doing that.
For 2 or 4 moves down the road, it still looks good.
Yeah, exactly. That's the thing. It still looks good like a couple moves down the road. Now, if I were to play like b4, then it would probably capture it. Let's see.
Yeah, let's see. Is there sound effects?
No, not yet.
Yeah, got it.
Okay.
Woo, yeah.
So yeah, that works. And like, if I were to play c3, I think it'd still capture it, but let's see. Because yeah, it did. So yeah, I guess it's very aggressive. So you guys have any questions? Yeah.
So first of all, thanks a lot. This is really cool stuff.
Yeah.
When you said high school, you meant grad school, right?
No, I actually meant high school.
All right. Second question, can it beat you yet? Can you play your own, creation, and is it defeating its master yet?
So I haven't actually played a game. I probably should, but the thing is, me now is a lot worse than like me before, because I used to play chess a lot in middle school, like competitively, but now I just code, I guess. I don't.
Third question, what are the limits? Have you daydreamed about the limits of machine learning? Like in, chess, it solves chess, but like in the problems that we face, like what to where to work and stuff, like where are the limits for machine learning?
So he's asking where are the limits to machine learning. For me personally, I think it's the fact that machine learning right now, it still like requires a lot of effort, meaning you still have to go get a bunch of data, curate it by hand most of the times, and like still mess around with the model. Like for instance, I had a model that legitimately was not working, and I had to mess around with it and realize that the learning rate wasn't going to do it. So things like that, right? I mean, you're not going to make Skynet happen if the learning rate isn't right? So
that's the goal.
Yeah, exactly. So it still requires a lot of like human and manual effort. So I would like to see in the future machine learning become smarter and more able to tune itself and more able to maybe not select its own data, but like better at getting data. So that's kind of where I would like to see it go. So that's the current limits. Yeah. Any more questions? Yeah.
Can you get like the chess engine playing itself and feed that?
Oh yeah. So he was asking.
To make it much better that way?
Yeah. So yeah, it's theoretically possible. I'm probably gonna try to tackle it next. It's so the thing is like obviously you need it to be a little good before doing that. So but yeah, it is definitely possible, which I'm probably gonna tackle next. Any more questions? That one in the back, I think. Okay.
Now, offhand, if you tried to compare this approach to old school kind of Minimax, how far ahead do you think your approach thinks? Can you follow me? Like, does it
So he's asking
ahead, etc.
How far ahead my approach would reach compared to traditional chess engines, I think.
Yeah.
So traditional ones would obviously beat mine right now because they're written in like C++, they're written in like extremely handcrafted code and whatnot, but like this has the potential to do a lot better because it's machine learning. But so I do think it has the potential to beat any chess engine, but as of right now, obviously not.
Yeah.
Any other questions? Oh yeah, that one right there.
Does yours improve itself as it plays? So if one would be to like train it with data that you already have in your model, would each game you play have the ability to store that in your database? Sort of?
So you're asking if, sorry, what?
Self-training.
Yeah, okay. So can it update its own database? Is that what you're asking?
Yeah.
There's like
Oh, okay. That would be interesting. You'd have to write rules for that. Probably something along the lines of if I lose, add it to my database, but there's obviously a lot of trouble with that too because some moves might still be bad. So that would be an interesting problem to tackle. But as of now, the database is pretty constant. Any other questions? Oh, okay. One over there.
So, in terms of things like sacrificing and basic strategy outside of just tactical reaction to individual positions, does this attempt any of that, or is it all just response of I get more material advantage this turn?
Oh, so it does have some, like in one, I remember playing it and I tried to get it into a fork and it got out of that. Even though like the way I was playing, like if you had taken a pawn, say it would have been a fork, but it didn't choose to do that. So it can do basic things because like it could look ahead and see that, hey, it's queen and rook is gonna get forked and that's bad news. So it can do basic things like that. But as far as like sacrifices and stuff, I'm not quite sure because there's some pretty advanced like queen sacks out there and stuff that, you know, you don't see coming. And so yeah, it can handle some basic strategy, but I don't know about that.
Theoretically, there's no limit.
Yeah, theoretically, I guess there's none.
So for the PGN database, not every case is good, right? So how do you separate the good cases from the when you train the data? How do you separate?
Oh yeah. So I had actually some problem with that, but what I basically did was I had two cases. Either if the material deficit was high, then I kind of knew who to give it to, like better for white or better for black. Meaning if white had way more pieces than black, it was obviously better. And if black had way more pieces than white, it was obviously better. But in terms of things in the middle, like since the Grandmaster games, if it's even, then I chose to give it to whoever last moved because I assume they're gonna, you know, they're planning something tactical and they're in a good place. So I'd like if white had just moved, I'd give it to white, even if it's even. If black had just moved, I'd give it to black. So this approach kind of worked, but it kind of didn't also. So I guess the only real way to do it would be like to go by hand and decide yourself. Again, going back to one of the limits I discussed in that I see like machine learning has. Anyone else?
We have time for one more question.
What time is this supposed to end?
55?
No, 50, I think.
All right.
We are out of time, sorry.
Okay. Thank you.